but they only go up to a certain level of technicality and then they cut off. And then beyond that, there is the technical literature, which is, intensely and deeply mathematical, but there isn't too much to bridge the gap between those two. And so my goal for this talk, which will be, sounds like a review for some and new for others, is to actually dive into some of those core mathematical concepts that drive the bizarre and amazing conclusions that we draw from the fact that quantum mechanics works. So the goal is going to be kind of twofold. One would be to give you a sense for how we want to maybe think about the mathematical elements that go into quantum mechanics and the assumptions that basically drive the theory. And then the second would be to give you a number of different reference points where, if you want to learn more about it, then with the little mathematical background I'm going to be able to provide now, then you'll have a chance to learn a bunch of different terms that you can Google for, or I'll give you some book references too that I found useful, and hopefully you can use this as a jumping off point into whatever area of quantum physics you want to. Probably it'll be useful to have some calculus and some linear algebra background if you're really going to dive in. You don't need either of those for what I'm going to talk about today. But if this is interesting enough that you want to pursue it further, those would be two starting points. And then depending on what your area of interest is, I can give you a lot of other pointers on things to look at. The other thing especially that would be useful is, this could be, for those that haven't taken a quantum mechanics course, this could be the launching point to either take a course or to read a quantum mechanics textbook. And I have a couple recommendations on that, but there are so many out there that you can basically peruse dozens and dozens of them, either here or on Amazon or what have you, until you find one that you think is a good fit for the way you think. Is it not working?
It's not finding it for some reason.
It's not finding it?
Well, it's probably because Mac and Windows formats are different, and you have to format the USB drive.
Should be. It's not. Here, let me try to transfer it again.
You can put it on.
No, you can just email
Email it to me.
Okay.
Mac and Windows played
Yeah,
together
but
better
it's-
now. They still don't.
But they should be. But it's OS X and Fedora should be compatible,
Oh, yes.
right?
Yeah, but it depends on how old your USB is.
That's pretty old. Yeah. Okay. Make sure I have it on there.
Is it even finding a USB stick? Yeah, it's not even recognizing.
Yeah, I mean, if you've got internet access, you could probably put it up on some public access like Dropbox or maybe a Google Drive and pull it down.
Let's see. Well, I guess we don't need. No, wait, we need it.
It's like, no, it's copy. Sounds like I just got bought out. Sounds like FBI. You got some
Can I try again? Okay.
She said that was really good.
Oh, gosh, it was the cardboard and, spray adhesive and fabric, hot glue. Yeah, it was great. So I brought a bunch of, I brought like, tabletop and curtains and, sheets and everything else with the costume. Just didn't know.
Did you manage to find anything?
No, I think anybody who wants to go to a serial killer themed costume has a good sense of
Yeah.
humor.
Wish it would be available. Yeah. That's what things would be.
That was so much fun.
That's nice.
It reminded me when we were talking about FBI because,
Try to use my mouse on this.
Gmail survive.
So you have other chickens or is there something fun? People with costumes. Parties.
Yeah, I have mine, but.
That's fun.
Okay, there we go.
There are a lot of recognizable officials like Charles Manson, Jeffrey Dahmer.
So I'm also experimenting with the presentation format, so I'll be curious to hear any feedback that you might have on that. So let's see, how do we get this to full screen?
Open the,
Go up, screen, it will pull down the menu.
This one?
View.
Okay, and then, oh, but can I zoom in this?
probably like a two-finger pinching on the track.
Oh, yeah.
This.
Not a touch on this? Oh, hey, perfect. Don't even need the mouse. Built for Mac. Okay,
And 3 fingers to move.
so 3 fingers to scroll?
Yeah,
Just swipe.
Okay.
and 2 is.
All right, I'm getting used to navigating here. Okay, so basically we've got 3 different aspects that we're going to touch on today. So we're going to go through a little bit of basic math, little math tools that some of you may already know. Then we'll get into the core principles, the assumptions, and the ways they're used in quantum mechanics, and then we'll go through some different applications and different areas that you might want to learn more about. So let's go here. So we'll start with complex numbers. So, and is that as far as it's going to let me zoom in? Can you guys see some of that? Okay. Oh, there we go. That's better. So complex numbers have a real part and an imaginary part. The imaginary part is denoted by multiplication with the number I. The number I is basically something that you take the set of real numbers and then you tack on this extra number I. And the purpose for I is that you can use that multiplied by itself to get a negative number. So that's why we use negative, and that's why we use these complex numbers. They allow us to have squares that are negative. So the real part and the imaginary part themselves are both real numbers, and then you just multiply the imaginary part by this I. One of the very common things that we do with complex numbers is we conjugate them, so we reverse the sign of the imaginary part, and that allows us to basically construct real numbers out of complex numbers by multiplying a complex number by its complex conjugate. And this always gives you the sum of 2 real squares, so that's going to be a real number that's greater than or equal to 0. And that's useful, for example, if we want the magnitude of a complex number, then that's just the square root of the product of the complex conjugate and the number itself. Another super useful piece of mathematical trickery with complex numbers is Euler's formula. Euler's formula you use a lot Basically, this is what we call a complex exponential. And it's got a real part and an imaginary part. And the real part is cosine of some angle, and the imaginary part is sine of some angle in radians. And you write that as e to the I times the angle. And if you want to take any complex number, you can basically take e to the real part, cosine, e to the real part times the sine times I. Now I'm being explicit about the times I here, just so you can see it a little bit easier, but later on I'll just do the usual multiplication where you put two numbers right next to each other, or two values right next to each other. This is a really counterintuitive formula. I really didn't believe it at first when I encountered it for the first time. And I think the best way to convince yourself that this is actually true is to look at series expansions for the exponential and trigonometric functions. So the exponential can be written as a series of increasingly smaller and smaller values. So it's just a sum of a bunch of decreasing values according to this formula here. If you're not familiar with the sigma notation, that just means you're summing all of the different terms. So you're summing for the n equals 0 term of this expression, plus the n equals 1 term, plus the n equals 2 term, et cetera, et cetera. So the n equals 0 term is this 1, n equals 1 term is x, n equals 2 term is x squared, 1/2 x squared, et cetera, et cetera. If you do the same kind of expansion for the cosine of an angle in radians, you get a lot of the same terms, but some of them have a minus sign in front of them. And if you do this for the same expansion for a sine, you get other terms that are also very similar to terms you have in the exponential. And what you realize is that you can use, all of these coefficients are the same. See, the 1 over 24 is the same in the cosine term, the 1 over 120 is the same in the sine term. And so all you need to do is figure out how to get some negative signs in when you square and cube these numbers. And the way to do that is with the complex unit I. So what we do is we say e to the I theta turns out to give you the right coefficients with the right signs. There's 1, and it's positive here, negative for the square, negative for the cube, positive for the fourth, positive for the fifth, negative for the sixth, and so on. And I've arranged these sums in this grid format to show you how all the different terms line up and match up with one another. So we're going to see this complex exponential quite a few times, and you'll see it. The more physics you do, the more you'll see it. So if you haven't seen it before, it's a little counterintuitive at first, but I find that it's one of the most useful and one of the most elegant mathematical tools there is. So let's zoom out. So we've talked about complex numbers. We've talked about Euler's formula for the complex exponentials. Let's talk now a little bit about vectors. So many people encounter vectors in high school or early college courses, and the way to think about vectors usually in those introductory courses is to think about them as little arrows. And the little arrows have a direction and a magnitude. And we can think about it that way too, but I want to give you a few more ways to think about vectors. So there's actually 3 different notations that you'll see a lot. The first one is these unit vectors, where you have a vector and it has different components. So if we're talking about a vector in space, which is normally the way you think about vectors on an introductory level, if we're trying to figure out the coordinates of this corner of the table, then if we start over in this corner of the room, then we go over some amount in x, and we go over some amount in y, and we go up some amount in z to get to the corner of the table. And in computer fields, a lot of the time people will use the vector term kind of casually as any grouping of numbers or data. But in physics it has a very specific meaning. And it has a meaning as something that's one-dimensional, that has some sort of invariant quantity no matter what coordinate system you use or what kind of transfer rotations, for example, you do on it. And what I mean by that is the position of the corner of the table should be the same whether you're using a coordinate system that starts in that corner over there, or if you're using a coordinate system that starts in that corner over there, and independent of what you call x, y, or z. So you may call x along the wall here behind me, you may call y out of the wall, and you may call z up. But I might call X, my X might be a diagonal along the body diagonal of the room, my Y might be a different body diagonal, and my Z might be a third different one. And we should be getting the same physics regardless of the coordinate system that we use. So one of the things you find is that when you start to write out these vectors in different coordinate systems, they always have the same dimensionality. So your coordinate system might have had three pieces to it, the X, Y, Z, and mine would also then have three pieces to it. And so how do we write out these three pieces? One way is with these unit vectors. So this is X with a magnitude of 1, Y with a magnitude of 1, and Z with a magnitude of 1, and then the numbers that they're multiplied by are the coefficients of the numbers. So it might be 6 feet in X, 3 feet in Y, and 2 feet in Z, for example. Those might be the coefficients. We can write that in a matrix notation too. We just have to understand that the first row is for X, the second row is for Y, and the third row is for Z. Those are the two most intuitive ways. In quantum mechanics, one of the notations that's used a lot is this Ket notation, which was invented by Paul Dirac. And I'll tell you why it's called Ket in a second if you don't already know. So it looks a lot the same. You've got the coefficients and essentially these unit vectors, except the unit vectors now are in this weird non-symmetric bracket. Okay? So we call the unit vector maybe for X direction 1, unit vector for Y direction 2, unit vector for Z direction 3, and then we have the same coefficients that you saw before. We can write this as a sum as well. And hopefully the sum notation will help you think about possibly having more than 3 dimensions to a vector. So if we're not talking about positions in regular space, if we're talking about some other concept that can be represented by vectors, we may have more than 3 dimensions to our vector space. One of the most common operations that you do with vectors is taking the scalar product or the inner product between 2 vectors, and you just multiply the corresponding coefficients together. So if I have a vector for a position there and a vector for a position over there, and then for some reason I want to multiply those 2 together, then I take each of the coordinates, multiply the coordinates, and add them together. So that's what you're seeing in this top sum. For those of you that know matrix notation, you can take the transpose, that's this T here of the vector, so turn this from a row vector into from a column vector into a row vector, and then use basic linear algebra formulas to get exactly the same result that we got with the other notation. So remember, we're not doing any new physics here, we're just talking about different notations. In the Ket notation, what you do is you flip around this asymmetric bracket, and so you take the Ket and turn it into a bra, and Dirac thought he was being very clever, so he just turned these into a bracket combination. And again, you've got the multiplication of the coefficients for each direction, and then you sum all those products. Now you'll notice here that I've got stars, and earlier in the notation we were talking about stars being complex conjugates. So in some cases here in quantum mechanics, you're going to find that the vectors are allowed to have complex numbered components, not just real components. And that is usually a little bit of a head scratcher at first, but turns out to give you reasonable agreement with experiment when you use complex coordinates this way. Okay? And again, it may not be complex in position, but it can be complex some other quantity that we'll talk about in a few minutes. So when we're taking the magnitude of a vector, it's a little bit like taking the magnitude of the complex number in a way. We take the magnitude of each coefficient and we sum those. So basically we take the dot product of the vector with itself, the scalar product of the vector with itself. And again, this is going to give you a number. So these are potentially complex numbers, but we're taking the magnitude and squaring it, so that's giving you a positive real number. And so we can, when we take 3 positive real numbers and sum them together, or they can be 0, of course. So non-negative real numbers sum together, we take the square root, that's going to be positive, or 0. So what we can do is, if we want to take these bizarre kind of abstract vector notions and get something real and potentially measurable out of them, we're going to need to take a magnitude of a vector. So the last thing I want to talk about is eigenvectors and eigenvalues. And this is a little bit more wonky than a lot of, at least initial courses on vector mathematics go into, but many of you may have seen these before. So the idea is that we start with a vector, which I'll call V, kind of like we were before, and we're going to operate on it with some kind of transformation. You can ask me what a transformation is, I'll show you an example in a minute. But the transformation basically takes a vector and turns it into another vector in the same vector space. And it can turn it back into the vector itself, it can turn it into some other vector, but the idea is, if you give it a transformation, if you have a transformation that you want to work with, then the transformation can operate on any of the vectors in the space, and it's like a black box, it just spits out what the new vector is. If the vector happens to be, if the new vector happens to be in the same direction as the old vector, even if it's pointed opposite, then it's called an eigenvector of the transformation. That comes from the German word for self or own, like your own vector. It turns you back into yourself, or some version of it. So it might stretch or squish the vector, but if it's an eigenvector, it won't change the direction. If it's not an eigenvector, then the direction will change. And so what happens is the transformation operating on the vector gives you a number, which can be a real number or a complex number, times the vector itself. And the eigenvalue is the amount by which then the magnitude changes. If the vector goes directly back into itself, then the eigenvalue is 1. If it doubles the length, then the eigenvalue is 2. If it halves the length, then the eigenvalue is 1/2. Right? And the last point, which is really going to be very useful for when we're talking about quantum mechanics, is it's often possible, if you have the same number of independent eigenvectors as you have dimensions in your vector space, then you can use the set of any of those eigenvectors, as long as they're all not parallel to one another. You can use those as a way to span the vector space. So that can be what's called a basis. Okay? So let me go back up and I'll talk a little bit about what a basis is. So a basis is a way of condensing information about some n-dimensional vector space into n independent vectors. And when you say that a basis spans the space, that means that any vector in the space can be written as the sum of those basis vectors in some way, multiplied by coefficients, which are usually real but can be complex. And just like I was saying that your xyz might be different than my xyz, you can choose usually from a lot of different possible basis vectors that span the space. So normally what you want to do is you want to choose the basis that works the easiest for whatever math you want to do. So you usually have a choice of which basis vectors you want to use. The only trick is they all have to be perpendicular or orthogonal to one another, usually. Well, it's easiest if they are. They actually don't have to be, but they have to be in some way independent of one another. But it's usually easiest to work with what's called an orthonormal basis. And an orthonormal basis is where you have all the basis vectors perpendicular to one another, and they all have a magnitude of 1. So the x direction, y direction, z direction is one example, very simple example of basis, and all of those three have a magnitude of 1 in an orthonormal version of a basis. So knowing that about basis now, let's go back and look at an example of how you can think about eigenvectors. So this is a bunch of colored dots, and I want you to imagine this as a group of vectors that span the entire two-dimensional space of the screen here. I didn't have room to actually draw the little arrows, if you like thinking about vectors as little arrows. So instead what I want you to think about is each dot represents the tip, the head of the arrow, where it ends. And every arrow starts at the origin right here where the two coordinate axes cross. Now the colors are chosen to show you the direction of the vector. So the reds go along the horizontal, the cyans go up and down vertical, purples are along the diagonal, up and down, right and left, and greens and yellows are along the other diagonal. So each one of these dots represents a vector, And if I want to perform some kind of transformation on this system, then it's going to change the vectors into other vectors. So here's one example of a possible transformation. And with this transformation, you can see that there are actually a lot of squishing and stretching going on. The horizontal is stretched and the vertical is squished. But there are two directions, the cyan direction and the red direction, that haven't changed. So those axes, the horizontal and vertical axes, haven't changed for this particular transformation. And so you can pick a vertical and a horizontal direction and turn those into your basis that spans the vector space. So here's an animated version of that if people want to, let me make this a little brighter. Here's an animated version of that if people want to see it. And we can change some things around in here to show you a little bit more complicated transformation. So here's the animated version, if you want, or maybe we should just pick it up and pass it around. Can everybody see that? Generally pass it around.
This is all 2D, right?
This is all 2D, yeah. So you can see we're doing that same stretch and squish that we had before, but now you can see it, the transformation actually taking effect, moving the vectors from one spot to another.
So the magnitudes are changing, but not the direction in X, Y?
Both are changing.
X and Y magnitudes are changing. The Y magnitude is squishing, so the Y eigenvalue is less than 1. The horizontal is stretching, so the X eigenvalue is more than 1. Anybody else wanted to see that before I mess around with it? So now we're going to make this a little bit more complicated transformation. And we'll see if we can still find any directions that are unchanged by the transformation. And that's squishing too much to see. Okay, so here's a different transformation. I'll just change the parameters of the transformation and see if you can find any directions where it might get stretched or squished, but it's still going in the same direction. So you can see now the axes are rotating. So the axes are no longer the eigenvectors. What do you think? You see anything?
The diagonal, this one.
Okay.
The blue one.
Yeah, the blue diagonal is squishing a lot, but it's not changing direction. And once you find one eigenvector, then it's useful to look perpendicular to it to see if you can find any others. And so you'll find that the other diagonal, which would be the yellow or green, is also not changing direction.
So this helps us to find the basis.
So we can use these eigenvectors as a basis, yeah. But the other thing it shows us is vectors that are unchanged in some aspect, direction in this case for this example. So vectors that are unchanged by a transformation, and that's going to be important in quantum mechanics also. So we're at 4:15, and that's the end of the first part. So I don't know if people want to take a quick break and come back, or if you have questions. The next thing we'll run into is we'll do the deep dive, the bulk of the talk on actual quantum mechanics rather than math.
So what is the significance of, or are you going to explain it?
Yeah, that'll be the very next thing. So just as a reminder, we covered eigenvectors and eigenvalues, vectors and complex numbers.
Yeah, I just had a question.
Yeah.
So this property that the eigenvectors are perpendicular orthogonal, is that that a property of a linear transformation? Or is it like if the transformation is always some kind of linear?
Yeah.
Then the.
Yeah, if you can find eigenvectors, then they'll be orthogonal.
For linear.
Yeah. Now you can choose bases that are not the eigenvectors, right? Because you could pick two orthogonal eigenvectors and put a linear combination of the two, and this could be your basis. But they wouldn't be, they'd be a basis, but they wouldn't be eigenvectors. So eigenvectors will be orthogonal
If the transformation is.
if the transformation is linear.
Okay,
Yeah.
perfect.
Vector or they're not, but vectors are scalable without distortion. And aren't.
So how new was the vector, eigenvector stuff for everybody? Was that something you've seen before? Is that pretty new?
I don't remember it. I remember vectors, but.
So the thing that we're going to do with quantum mechanics is it's so easy to think about vectors as little arrows in space, because that's the natural example of a vector. And we're going to throw that thought process away. We're going to think about sort of abstract concepts in vectors. So if you're really fond of three-dimensional space, real space will still have 3 dimensions in quantum mechanics, unless you want to go deep into string theory. But the vectors that we're going to be talking about in quantum mechanics won't necessarily be limited to 3 dimensions. They might have quite a lot of dimensions.
Aren't they necessarily spatial dimensions either?
No. Well, usually they're not. Usually they're not.
So more than third dimension would go into other than space, or?
Well, they won't necessarily be talking about space or position, but there'll be a way of basically bookkeeping. So we'll get into that when Paratosh gets back. Okay, so now we're going to get into quantum mechanics itself. Now, there are a lot of different notations for quantum mechanics, just like there are a lot of different notations for vectors. I'm going to show you one that's very common. Let's see if I can. If you want to see different approaches, there are so many to introducing quantum mechanics, and I'm going to follow an approach out of this book, mostly, which is a classic textbook. Another quantum mechanics textbook that I've used that follows a very different approach but reaches the same conclusions is this one. And there are tons and tons and tons out there. So hopefully this will help build an intuition, but this is not the path historically along which quantum mechanics was developed, nor is it kind of a conceptual easing in from classical mechanics to quantum mechanics. We're just going to dive right in, and we'll come back and I'll talk just a little bit about one of the problems that helped to motivate the development of quantum mechanics. But here we're going to talk about quantum mechanics as it is fully formed. Oops. So the main idea in quantum mechanics is that you have states and you have operators on those states. And the states are represented by a vector, as we were just talking about vectors, and the vector will have a magnitude of 1. So in your normal thinking about vectors, the vectors have different magnitudes, but for it to be a state in quantum mechanics, it has to have a magnitude of 1. And the operators are represented by transformations on the state vectors. So remember, I said that that the transformations take vectors to maybe other vectors, right? So operators are these entities mathematically that transform state vectors. And if it's an operator that has some correspondence to an actual measurement that you could make, then we call that kind of an operator an observable, because it's something that you could actually do a measurement to take a look at. The possible outcomes for an observable are a basis that spans the state space. Okay, so this is really key. So think about, if you take a measurement, then the possible outcomes basically are let's say you have n possible results of the measurement. Then the way that you keep track of the state of the system mathematically is to have an n-dimensional vector that you carry around with you, so to speak, mathematically. And that vector spans, or the possible measurement outcomes are a basis that spans that vector space. So if you have 8 possible outcomes, let's use an odd number. If you have 5 possible outcomes, because there are actually systems that have 5 possible outcomes in quantum mechanics, then you have a 5-dimensional, what's called a Hilbert space. And a Hilbert space is just a fancy name for a vector space. So your possible outcomes span that 5-dimensional space. Now, if you're talking about position is treated as having an infinite number of outcomes. So if I measure a position of a particle, it could be here, it could be here, it could be anywhere in between, it could be over here, it could be over here, it could be over here. And for every possible here, you're giving the state vector another dimension. So you have infinite dimensions in these vectors that you have to keep track of for things like position and momentum, which is a little bit crazy sounding already, right? But it works. So if the variable is continuous, then it's going to